Okay, welcome back to our notes on forces. Today we're going to talk about net force, and I introduced this idea to you before, but we're just going to go a little bit deeper in and see some of the finer points of what calculating a net force means in terms of the motion of an object. Remember that the net force is otherwise known as the sum of the forces, sum being SUM, when you add something up, what you get at the end of all the addition is the sum. So the sum of all the forces, the product of the addition. The net force, the sum of all the forces, affects how an object moves. Individual forces are added up to determine the net force. That's why last time we wrote all those net force equations. Our first example today is going to be a car that is parked. The force of gravity on the car has a magnitude of 2,000 newtons, and the force from the ground on the car has a magnitude of 2,000 newtons. Let's draw a free body diagram to show these forces. So let's remember our steps. My first step is to draw a dot and label it. In this case, we're dealing with a car. My second step is to draw an axis to show the positive and to show the two positive directions. I'm going to use my standard axis with x pointing to the right and y pointing up. Those are the positive directions for x and y. Now I draw my forces. The force of gravity on the car, remember, it's the interaction between Earth and the car that causes that force to be put on the car. So the Earth is really the other object in this. Well, the force of gravity is going to pull the car down towards the center of the Earth. So we're going to label this, you know what? We're going to start using the symbols in some cases, we're going to start using the commonly used symbols for these things. So instead of writing out F gravity, I'm just going to write F and then G. It can be an uppercase G, it can be a lowercase g, but F sub G is the well-known symbol for the force of gravity. I don't quite want to reveal the symbol for the force on the ground yet, because I can't call that Fg, so I'm going to continue calling this F ground. Okay? Because remember, that's the force from the ground on the car. What is the net force on this object in the vertical direction? It looks like those are the only two forces on it. Okay, we have this car that's parked, nothing is pushing it left or right in the x direction. We simply have two vertical forces. We write out our net force equation, so we write F net y equals, what's the force in the positive y direction? That would be F ground, the force from the ground on the car, minus Fg, the force of gravity acting on the car. Again, remember that comes from the Earth. I actually, this time, have numbers that I can plug in and I can calculate what the net force in the y direction is. The force from the ground on the car is 2,000 newtons, and the force of gravity is also 2,000 newtons. So the net force in the y direction is 0 newtons. And notice what that says about what the car is doing. The car is motionless, and it happens to have a force of 0, a net force of 0 on it. That doesn't mean anything that's motionless always has a net force of 0, but it is interesting. This car is staying parked over time, and the net force is remaining 0 over time, unless we have something else going on. Okay? Whenever an object has a net force of 0 on it, we say that it is in equilibrium. E-Q-U-I-L-I-B-R-I-U-M. Equilibrium. Equilibrium means that the forces acting on the object are balanced or are equal to each other. I guess saying they're equal to each other isn't necessarily great. The forces are balanced gives a better impression. That you have equal forces in one direction as you do in the other direction. If you have 2,000 newtons of force pushing up, you must have 2,000 newtons of force pushing down as well. Okay, so that's what equilibrium means. It means net force of 0. You have to associate those in your head. Equilibrium means net force of 0 newtons. We're going to see as we go on that it has some other implications as well. Let's consider the same car while it's moving this time. We're going to keep the same forces. The force of gravity on the car is still 2,000 newtons. The force of the ground on the car is still 2,000 newtons. But let's say the driver also presses down on the gas, which causes a force with a magnitude of 500 newtons to be generated between the tires and the road. At the same time, the magnitude of the force of friction on the car is also 500 newtons. So let's draw another free body diagram for the forces on the car this time. Okay, here's my car. Here's my axis. I'll keep the standard axis going, x, y. I'm going to have a force upwards from the ground, F ground. I'm going to have the force of gravity, I'm going to call that Fg. I'm going to have the force forward between the tires and the road. And again, what that's really caused by is the gas combusting in the engine. So let's call that F gas. And there's also a force of friction on the car. So I'm going to write F friction, or I'm actually going to abbreviate this one. I'm just going to call it F with a F sub F, F with a little F next to it. That is a standard accepted notation for the force of friction. That's my free body diagram. If I want to scale this so that the vectors represented how, if the vectors represented the size of the forces, I would have needed to have made the F ground and Fg longer than the vectors for F gas and FF because they are greater, 2,000 as opposed to 500, but I didn't. What is the net force on this object? Is it in equilibrium? Well, in order to determine that, remember, equilibrium means net force of 0. We need to write out our net force equations to figure this out. F net x equals F gas minus FF. And what's that going to be equal to? F gas is 500 newtons minus the force of friction, which is also 500 newtons. That's equal to 0 newtons. In the y direction, we have F ground minus Fg. And, just as before, that's going to be 2,000 newtons minus another 2,000 newtons, so it's 0 newtons. So in this case, the car is in equilibrium in both directions. Now this might be a little bit confusing because of what we said about the car when we went to do this first free body diagram, or the second free body diagram, I should say. We said consider the car while it is moving. And for some people, this raises alarm bells. They see that it's in equilibrium, they see that there's no net force on the object in any direction, and they automatically think that it must be at rest. But I am telling you right now that the car is moving. This seems like a paradox. This seems like an oxymoron. But it's not. Okay? Just because something is in equilibrium does not mean it can't be moving. How is this possible? Well, let's go back to the simulation that you guys looked at in class, the FET Forces and Motion Lab simulation. So here's what we're going to do. We're going to take a look at this simulation, and you can see right now the object is at rest. There are no forces on there. I have the forces, once they get generated, they'll show up like this. There'll be little arrows, okay? So let's have this guy put a force on our box, and you can see that now there's a force. This is, by the way, frictionless, okay? I can increase that force, and we see that the speed increases a lot. Oh, that's not what I wanted. Okay, anyways, the object is moving at a pretty good rate now, and look what I did. I took away the force on it. Remember, there's no force of friction. There are no forces in the horizontal direction on this box right now. And notice what's happening. It's still moving. And notice specifically what's happening with the speed. The speed is remaining constant, okay? Or you could even say the velocity is remaining constant because neither the speed nor the direction are changing. Watch what happens when I put a net force on the object. Remember, if I just put an applied force on there, there is no force of friction, so then, therefore, that must be the net force, okay? That's the only force in that direction. If I put a force on there, look what happens to the speed. The speed is decreasing. Matter of fact, you can tell it's decreasing by quite some amount because you can tell visually that's slowing down. I take that force off, and now it's moving at a constant velocity again. This is crucial. Okay, this is very, very, very important. Okay, there we go. All right, so even though there is no net force on the object, the car can still be in motion. How is this possible? We just saw that if we have an object that has no net force on it, it could be at rest, that's true, or it moves at a constant velocity. The velocity does not change. In other words, if the velocity is not changing, that means that the object is not accelerating. Because remember, acceleration means a change in velocity over some period of time. It instead moves at a constant velocity. So just because an object is in equilibrium with a net force of 0 on it does not mean it is at rest. It means that it is moving at a constant velocity. That constant velocity could be 0, but the velocity is constant, and that is the important part. A net force of 0 does not mean that an object must be still. Instead, it means that the object is simply not accelerating. And again, remember that accelerating means changing velocity. Well, let's look at the converse of this argument. If a net force of 0 means that the object is in equilibrium, and therefore the velocity is not changing, and therefore it's not accelerating, what does a non-zero net force mean? Non-zero means anything but 0. Okay? Positive, negative, fractional, huge, whatever, anything but 0. A non-zero net force means the object is not in equilibrium, which means the velocity must be changing, which means it must be accelerating. A non-zero net force on an object causes a change in velocity, which we call acceleration. So, we just spent a whole unit talking about how sometimes objects have accelerations. Why do some objects accelerate and some objects don't? The objects that have acceleration have a non-zero net force on them. The objects that do not accelerate, that have a constant velocity, have a net force of 0 on them. And again, remember, you can accelerate in one of two ways. Either your speed, or the object's speed, or direction, let me move this up for you, changes. Okay? Either the object's speed or direction changes. So, a net force of 0 means the object's in equilibrium. If the object's in equilibrium, then it is not accelerating, which means the velocity does not change. Everything is the opposite for a non-zero net force. It is not in equilibrium. There is acceleration, therefore the velocity changes. These ideas were stated very, very famously by this guy right here, Isaac Newton, founder of modern, you could probably call it the founder of modern day physics, or founder of modern science. Not founder, but one of the great figures. What Isaac Newton said, and I'm going to paraphrase a little bit as I go over this in class. A body, by which he meant some object that is at rest, will remain at rest unless acted upon by an outside net force. Some net force originating outside the object. A body in motion will remain in motion unless acted upon by an outside net force. So essentially, objects will continue doing whatever it is that they're doing unless a net force acts on them. In other words, objects don't accelerate, change their velocity, change their speed or direction, unless a net force acts upon them. Okay, unless some other net force comes along, gives an acceleration to change that velocity. This idea is known as Newton's first law. Very famous. We're going to go over the next two laws somewhat soon, but you should know at this stage which law is which. Okay, the first law, Newton's first law, is an object at rest stays at rest unless acted upon by an outside force, and the same goes for an object in motion. Very quickly, before we finish up, I want to make graphs for what an object in equilibrium and an object experiencing net force would look like. We're just going to kind of sketch out what they would look like based on our ideas of what equilibrium is and what net forces do to objects. So we're going to have graphs of acceleration versus time. We're going to go kind of backwards. So acceleration versus time, velocity versus time, and then distance versus time graphs. Okay. An object in equilibrium has no net force on it, and therefore we said that there's no acceleration. So what would we expect that graph to look like? Well, if there's no acceleration and we have a graph of A versus T, then the A has to be 0 throughout. So I would just kind of maybe emphasize that the acceleration is 0 by kind of shading in this line very heavily. Okay, there are no data points above or below the x-axis. The acceleration is always 0. If there is no acceleration, remember the definition of acceleration. Acceleration means that an object is changing its velocity. So if there's no acceleration, that means the velocity cannot change. So your v versus t graph should show no change in velocity. And let's think about what that means. If there is no change in velocity, if the acceleration is 0, we know that for a velocity versus time graph, the slope is the acceleration. If the acceleration is 0, then the slope must be 0. Remember, a slope of 0 is just a flat line, okay? Not a line with a measurable slope, but a flat line. So we're looking for a slope of 0 here. There. That velocity is definitely has a slope of 0. The velocity is some positive number. The object is moving, but the slope of the graph, the slope of the best fit line is 0. So we could have this, or perhaps we have something like this. Here's v, here's the time axis. This is also a slope of 0. It just so happens that the actual value of the velocity is also 0. This object is moving forward at a constant velocity. This object is at rest. It has no velocity. The velocity data points all say 0. We could even have an object with a negative velocity that is constant, like so. Okay? That just means the object is moving backwards at a constant velocity. Okay? That's all the negative means. It just happens to be moving backwards. So, if the velocity is constant, remember that for a d versus t graph, the slope equals the velocity. So if the velocity is constant, therefore the slope of a d versus t graph must also be constant. A constant slope is just a slope that is the same throughout, the same steepness throughout. So that could look like this. That's the same steepness throughout. Okay, it doesn't change in steepness. You could have something like this. That's the same steepness throughout. Or you could have something possibly like this. Okay, I have a positive slope here. I have an object moving forward. I have a negative slope here, an object moving backward. I even have an object. This is still a constant slope. It just happens to be a slope of 0. This is an object that is at rest. Okay, and what I really should have done is I should have drawn this one here and this one here so that we could match up all of these. Okay, because this graph, these two graphs match up. Constant positive slope. Slope means velocity. Constant positive velocity. Here I have an object that is not moving forward. The slope is 0. Slope is velocity. Here I have velocity of 0. Here I have a constant negative slope. Here I have a constant negative velocity. So I should have drawn these in a little bit better order. I apologize. Okay, but these graphs, every single one of these, represents an object that is at equilibrium, that does not have a net force on it. Now let's look at what happens if an object is experiencing a net force. We'll do the same order. A versus t, v versus t, and d versus t. Okay. So, if it experiences a net force, it's not in equilibrium, which means it is accelerating. So now we can't, the only type of graph we can't have is one that looks like this. We either have positive or negative acceleration. And we're going to restrict ourselves to talking about constant acceleration, so accelerations that don't change. So here's an example of an acceleration that doesn't change over time. It remains at the same value. Or you could have this. That first one is an example of a positive acceleration. Here's a negative acceleration. Okay, there you go. Now, if the acceleration is non-zero, then that means that the slope of our velocity versus time graph, which represents acceleration, should also be non-zero. In other words, we need something with some steepness to it. Another way to think about that is we need the velocity to be changing. The value of the y-axis should be going up or down. There's a non-zero slope. It's a constant slope. Don't get that confused. It's constant because the steepness is the same throughout. What is key here is because the acceleration is non-zero, the slope of the v versus t graph should also be non-zero. In other words, it should have some steepness to it. It should not be flat. This would also work. There's another non-zero slope. Now, could I have something where these traces are below the x-axis? Yes, but in the interest of time, I'm not going to draw those. So if the velocity is changing, remember, the slope of a distance versus time graph is the velocity. So if the velocity changes, then the slope of the distance versus time graph should change. It's very key that you keep in mind what all of these different slopes mean. And that you really understand the difference between words like constant and zero, positive and increasing, negative and decreasing. These words are not interchangeable. They have specific meanings. If I need to draw something with a slope changing, that means the steepness changes. That could look like this. That might look like this. That could look like this. That could look like this, or any other number, okay? But the key here is that the steepness of all of these lines, the steepness of all these curves is changing, okay? So, key ideas with net force. Net force is the sum of all the forces. We can determine what the net force is by figuring out the value, the magnitude of all the forces, then putting them in the net force equation and seeing what we get. If we get a non-zero, or if we get a net force of zero, the object is in equilibrium. There is no acceleration, and the velocity does not change. On the other hand, if we get a non-zero net force, the object is not in equilibrium. The object must be accelerating, which means the velocity changes. Okay? Those are key facts that you have to know in order to do well in this unit. All right? They're pretty easy to remember, but you have to make sure you apply them correctly. We're going to continue with our discussion of net forces in the next video.